Well, thank you very much. I hope I live up to that welcome. I'm going to give you a lecture which I normally give to children of all ages, i.e. from about 6 to 80, and it's called Braving the Elements, and it's about what chemistry is all about. But I only have 40 minutes now, and so I've selected things from there and tried to give them a Christmas theme. Now, the first one is really just to remind most of you, if you ever studied chemistry or you are studying it now, that you probably first of all come across chemical reactions in the form of ionic reactions, acid-base reactions. You mix an alkali with an acid and you form a salt and water. And it's less than spectacular because it's a colorless liquid turning into a colorless liquid. Maybe we won't do that. I will do it for you, however, using an indicator, which is what you learn at school, a substance which changes color when you go from acid to base. And I'm going to do it in a fairly unusual form, but it's a very, very appropriate way of doing it, given that the United Nations Climate Change Conference is still on, and I know that because my daughter's there as a delegate. And so what I'm going to do is I've got some different indicators here, and this is a mildly alkaline solution, right? And so they're the appropriate colors for alkali. Now I'm going to add a substance which we've all heard of, and that is carbon dioxide, but I'm adding it in, not from the air, but in a solid form. So I have some solid carbon dioxide here. I put on the end. You can see it's an unusual substance in that under the conditions of this room, it turns directly from a solid into a gas. There's no liquid form under these conditions. So what I'm going to do is simulate a kind of third-rate science fiction movie, and I'm going to add some of that to each of these. And I want you to tell me if you can see anything happen. I washed that one out before, and obviously I didn't get all the washing up liquid out of it. Never mind. Actually, it's quite a pleasing effect, isn't it? Maybe I'll do that in future. Well, something should be happening somewhere. Did you see this one go? It changed color. I'll put a bit more in just to remind you. And one of these will change color as well, and I can't remember which one. This one changed, did it? Yeah, I thought so. No, I'm excused making that statement. I'm totally red-green colorblind, so I can't tell colors very well. I could tell that color change. Now, let's fix on the ones that did change color, and you saw it change color. Why did it change color? Because the carbon dioxide dissolved in the water to make a mild acid, carbonic acid, and that neutralizes the carbonate until eventually all the carbonate is gone, and the sodium carbonate, and then you get just the carbonic acid, and so it changes color. Why does this one not change color? Well, because you needed a much stronger acid for this to change its color. So two of them changed, two of them didn't. Why is that important? Everything you read in newspapers is concerned, in terms of climate change, with change in temperature and what's going to happen, change in humidity. In fact, I think the thing we should be worrying about is exactly that. Because we know, one of the few facts we absolutely know is that carbon dioxide levels have risen dramatically over the last century, and then the carbon dioxide dissolves in the water, and it acidifies the water, the oceans. And creatures that have shells cannot lay down their shells except in alkaline conditions. And there are already signs that they're under stress. And if this continues, you will wipe out that level of sea creatures on which many fish rely, and we rely on the fish. So there's a major catastrophe headed our way, and there's no argument about it. The change in pH is being measured right now, and it's real. So forget the dispute about climate change, worry about this. All right. that was a very simple chemical reaction, just to be topical but not Christmassy. Let's move over here and do something different. What do we do at Christmas? Well, the adults amongst you, and I dare say a few of the younger ones too, tend to drink alcohol, don't they? So let's just drink a little alcohol. Now, I'm very fond of red wine, and so you have to stretch your imagination to think that this is red wine. So I'm going to pour some red wine out, all right? Now, personally, I wouldn't drink that. I was once served some wine of that color in Greece, and it tasted pretty much as you might imagine it would have tasted. But perhaps at this time of the night, and given that I've still got to lecture a little longer, maybe I should be having white wine, not red wine. So why not have some white wine? Some of you may not approve of alcohol, so maybe you'd rather have some milk. So let's see if I can give you some milk. Actually, I hate milk. I can't drink milk on its own. I can drink it when it's flavored. So maybe a raspberry milkshake would be the right thing for me. There you go. But my favorite tipple of all, as Peter probably knows, is champagne. So why don't we have some champagne at the end, okay? All from the same bottle, right? Now, those reactions are spontaneous. They happen, two ions just have to collide together for those reactions to take place. And so they're diffusion controlled, as we say. There are really two sorts of chemical reactions. There's those reactions which require an energy source continuously to make them happen. And there are others which are spontaneous, if you like. They're energy releasing. They give out energy, and I'm going to show you some of those in a minute. But they require a tiny amount of energy to get them going. That's called an activation energy. So by and large, most reactions require some sort of energy to get them going. And we could ask ourselves what sort of energy we could use. Well, the one that you're most familiar with, of course, is heat. And so we can use heat to initiate reactions, and I'll do that in a minute. Any other forms of energy that people could think of? Light, yes, okay, we'll look at light. Anything else? Electricity, did you say? If you said kinetic, which I think you may have done, that's just another way of saying heat. I mean, that's the same thing. All right, so let's just stick with those two, because we haven't got too long, have we? So let's do electricity first, all right? I'll move these out the way so you can see. I need a volunteer for this, so, well, he was first, actually, so I'll take you. Also very agile. Why don't you come round? What's your name?
Alex.
Alex. Have you got any heart complaints or any? No. All right. Good. Good. And you're quite brave, I know. All right. I would like you to just cup your hand if you can. No, just one hand, because I'm going to pour some liquid in there. It's just washing up liquid. Can you see? Washing up liquid. It doesn't nothing corrosive. So there we go. And I'll give you something to wipe your hand with afterwards. Now, I'm passing electric current through this extremely expensive vessel that I made earlier. And now I'm going to blow some bubbles on your hand. Can you just hold that there on your hand till we get some bubbles? Because I have to look for another piece of apparatus. Is this? So down we go in there. Right, ready? 1, 2, 3. Good. Now he knows what's coming. We'll do it again, shall we? Well, I did call this lecture Chemical Christmas Crackers. Did you see the caption as you came in? Was it up there? Yeah, okay. Behind me. Oh. Right, here we go. Let's do it again. And now it won't even go bang now, will it? Come on. No, it won't if the match doesn't work. Oh, that's a bit more feeble. Well, sorry about that. Good. Hang on a minute. We've got... I had some stuff to wipe your hands with, but I don't know where it's gone. Can you see it? Oh, here. That's it. There we go. Just off you go there. That's good. Well, I think that's a round of applause for that. So, electricity is useful in that regard. And of course, what I was doing is I was just splitting water, in fact, and then recombining it. So I needed energy to split it, and that was the electrical energy. And when it recombined, it gave out energy, and that was the little bang that you heard. Okay, so that's, if you like, using electricity. Electrochemistry is a branch of chemistry. What about light? I mean, I have to say I'm hung up on light because I've spent my whole career using light as an energy source to drive chemistry and other things. So I think we should sort of turn to light and see just a few of the properties. Now, why would we want to use light? Well, I need to show you that light is a form of energy first. And sometimes this works. It depends how bright the lights are up there. With a little additional... it's trying. Come on, you can do it. Just beginning to go. Can you see it? Well, I need to get a little bit nearer to that light up there. Where's another light? I didn't bring the very bright light source with me, so maybe if I move up and hold it up there. Oh, now it's going, right? Can you see it going now? Accelerating away. Well, it's not. There we go. You all see that? And if I take that away, it'll stop. Should stop. Well, there you are. No, it is stopping. Right. And so the only energy source going into there is the light from either this torch or the lights up there. And it's this is made by BP, who's invested quite a lot of money in solar energy conversion, photovoltaics. And that is converting the light into an electrical current, which is driving a little motor, which is making it go round. So light is a form of energy, and it doesn't take much energy to make this thing work. Easy to make light. Now I need to switch the lights off without garrotting myself on these things. You're going to do it for me. That's excellent. Could you put them right down as far as possible, please? There we go. Oh, that's fine. All the way out. That's good. So this is just a little plasma globe. I've got a big one, but it didn't seem to want to work, so I'm going to use a little one, which I know does work. So we're passing a radio frequency discharge through a gas. We're making the gas excited, and I'll show you what that is in just a minute, how that happens. And when the gas relaxes, the ions in the gas relax, they give out light. Now, if you notice, if I put my finger on the top, can you see the stripe going to my finger is brighter than the others? Is that obvious? So if you think about it, you're all scientists, what does that mean? Well, it means a bigger electric current must be going down that pathway than down the others. So that electric current must be passing down through my arm, through my body, and into the ground. And yet I'm still standing here. Well, you know very well if you stick your fingers in an electrical socket, it's the last thing you'll ever do, because it will kill you. But I'm, so far, so good, not expiring. And if you want any proof of that, I've got in my hand here just an ordinary fluorescent light tube, okay, which you know these things don't light up spontaneously. But if I touch it near there, you see it lights up quite nicely. Now, so again, I've just proved, I think, that it must be, the current must be traveling through me and down to the ground. I'm earthing it. And just to finally prove that, if I hold it halfway down, only half of it lights up, all right? So, a good proof. So, the efficiency of converting things into light in tubes like this is really quite good. And this is a little laser I have, a little solid-state laser. I remember how to switch it on. There we go. And you can see it's green. This is actually illegal. I shouldn't be using it in an audience, but it's only 5 times over the limit, so I think I get away with it. It's Chinese, if you want to know. Now, Peter will appreciate this. When I first started working in photochemistry, we got one of the first lasers for that purpose in the country in about 1970. And it was an argon iron laser, and it had a power supply about as big as this bench. And it took 3-phase electricity in to get it to work, and it produced about the same amount of power as this little thing that I've got here. And this runs off little penlight batteries, and I haven't changed them in 2 years, so, you know, it's pretty efficient. So we've come a long way. So it's easy to make light. Why would I want to use light rather than anything else? Now, I did have a very expensive piece of apparatus to illustrate that, and this is one of these things I brought from the Royal Institution years ago. It was made for me, so I felt no compunction about stealing it from there. So I want you to imagine that this is the simplest possible form of matter in the universe. This is the hydrogen atom, all right? Well, a chemist would say that. And so it has one proton, one positively charged particle in the nucleus, and it has one electron which travels in space around it, all right? Now, in fact, it travels in 3 dimensions, not 2, so it travels in a spherical pathway, if you like, fills a sphere with a charge. And all that happens when light comes along, of the right energy, the right color, right frequency, is that the electron simply jumps from one place to another, all right? So there are some things wrong with this model, which I'll tell you about in just a minute. I want you to imagine what would happen if the electron, now it's excited, has a lot of excess energy, so it drops back to the place where it came from. If light is absorbed going up, light must be emitted coming down, all right? And I'm going to show you a few of those things. All right. So what's wrong with the model? I mean, it works. I was going to set up this ultraviolet lamp here so all you could see was the ball in the middle, but I didn't have time, and it actually hurts my eyes, that lamp, so I'm quite happy not to be doing that. What's wrong with this? Well, the size of the nucleus, for a start. If this electron was actually filling the space in Wembley Stadium, 3-dimensionally, then the actual size of the nucleus would be the size of a housefly placed at the center spot of the so it's very small. So this is a bit wrong. And the other, as Peter will well appreciate, is that transition is actually electronically forbidden. It cannot happen. To go from a sphere to a sphere, a spherical distribution to a spherical distribution is not allowed. So I should be trying to make this trace out a kind of dumbbell shape, and I can't do that. I did try, but I can't do it. So you'll have to be content with a forbidden transition. Now, why would a chemist be interested in that? Well, this happens in molecules as well, of course, and the colors that you see around you, let's pick on somebody, and I have to be careful here because I am colorblind. That looks red to me, is it right? Looks red because all of the colors of the rainbow from the source up here are being absorbed by the dye in your sweater, except red, and the red is being transmitted. So all of the molecules of dye in your sweater, all that's happening all the time is the electrons are jumping from one place to another, and that gives rise to the absorption. And then they come back through other processes. Blue, because the red end of the spectrum is being absorbed. Well, a chemist would know that what makes how you understand chemical reactivity, how a molecule reacts, is where its electrons are. What is the electron distribution like? And that will allow you to rationalize the chemistry that happens. When you take an electron here into another place, the electron distribution has changed. It's not the same as the molecule in its lowest energy state. And therefore you get quite different chemistry from the excited state than you do from the ground state. And you can do things with light you cannot do with heat. And that's why we're interested. But other things happen too. Well, maybe I'll show you a chemical reaction first. What sort of things are we interested in at Christmas time? Well, babies, I guess, is one of the reasons we celebrate Christmas. A baby. All of you were babies once, some more recently than others by the looks of things. Any of you happen to know when you were first born you had jaundice? You were jaundiced. One there, one there. Actually, in an audience this size, there probably will be about 30 of you who had jaundice. You wouldn't remember, of course, because you'd only be 1 or 2 days old. Well, the treatment for jaundice is to simply shine a blue light on the baby. Blue because the jaundice gets its name because you turn yellow. You have a yellow color in your skin. And that's caused by a substance which, when red blood cells are broken down in the body, they're old ones, that we don't need them, they break down in the body, and they produce this bright yellow substance. Now, you get rid of it, in a way that will become obvious, and you have an enzyme in your liver and bile which converts this bilirubin, which normally will not dissolve in water, it converts it into a water-soluble form, so you can get rid of it. A newborn baby doesn't have the enzyme because it didn't need it. The mother was doing the excreting, not the baby. And so it has a problem. It is making lots and lots of this yellow stuff, breaking down the red blood cells, but it can't get rid of the bilirubin until it gets the enzyme. Well, it takes a day or so for that to happen, but sometimes it takes much longer. And all the time you're making this yellow stuff, it dissolves in fat, and you have a lot of fat just under your skin. That's where it goes, and hence the jaundice. So I thought we might show a real baby undergoing this treatment at this point. So all the time I'll be speaking, I was going to decorate this as a crib, but I didn't have time, and probably a bit blasphemous anyway to be doing that. So I will just content myself with showing you the real baby. And he is my constant companion. He's been with me many years now, travels all over with me, and you see that he suffered a major catastrophe in about a couple of years ago now. I took him to Toronto, and British Airways thought it would be fun to throw him around all over the place, and he didn't quite survive, but he was fixed by the blast flow in Toronto. Well, what's most noticeable about this baby is, apart from the fact that it is a male child, which obviously you've all just seen, in his legs he has the authentic material which causes jaundice in newborn babies. This is bilirubin, so-called. Now I want to show you that he can't get rid of this, so I'm going to give him a drink, and it would be easier to give him a drink if I had a funnel, and here I have a funnel. So let's just, he drinks, never complains, this child, he's very... When I hold him up, it'll be his, the water will be the top layer. I better switch that off. And I think you can probably all see that the bilirubin is still in the legs, so he's still a severely jaundiced baby. And he might die unless we do something to help him. They did used to die in the 50s. Well, all we do is we irradiate him with blue light. Blue, because this color yellow, is because of the white light that's incident. The red and the blue are being absorbed, and the blue is more energetic, so I'll use that. So there's enough blue light in this to do what I want. Now, there's some interesting chemistry here, but I'm not going to bore you with it. But the reaction which takes place is very much the same sort of reaction as occurs in your eye, giving rise to vision. The twisting of a molecule about 100 through 180 degrees, one part against another, and it's a reaction which is impossible to do thermally, as is the reaction in your eye. It's just as well when you think about it. If you had a thermal fog all the time, you wouldn't really have good vision. So it's a purely photochemical process. Now it should take 2 minutes, and I haven't been counting, so we'll give it a chance. I have to do something now I wouldn't dare do in Massachusetts. I have to shake him violently. And even that short irradiation, if I've got it right, should be enough to do exactly what happens in your body. And as you can see, it now has dissolved in the water. So now he can do exactly what you do, although those of you whose physiology resembles this, and he can excrete his bilirubin. Well, other things, as I said, luminescence happens when you excite molecules. They can give out their energy by giving out light. And so I want to show you just a couple of things relating to luminescence. I've got a whole range of dyes here, laser dyes in fact, which can, in fact the one I wanted isn't there. Oh, is it? No, didn't bring it, never mind. I'll have to use the other thing instead. Right. Let's take that off. Can you just dim the lights right down, please, so we can see this? So you see all the colors there, and then when I irradiate, you can get a whole range of different colors, depending on which dye you actually use. Now, there is one which is interesting, which maybe I did bring along. Oh, there it is, yes. This one's interesting. You see it's colorless, all right? No color. So it's not absorbing visible light. But all molecules must have electrons somewhere, and so they must absorb. This one absorbs in the ultraviolet, and so it does fluoresce, and it fluoresces a bright blue, as you can see. And the kind of things we put in fabrics are exactly this kind of thing to make them look brighter than white, or whiter than bright, or whatever the ad says. Well, here's a substance which I'm going to say is I'm very fond of at Christmas. Actually, I'm very fond of every day, so I have to be honest about this. So here we have just an ordinary kind of tonic. And with the lights down, it may surprise you to see that this has a bright blue fluorescence. It has quinine in it, and it's the quinine which fluoresces. Now, it's not too different from that, is it? But I really would not drink this, because it is a carcinogen. It would give me cancer, diphenylanthracene, and the solvent is methanol, which would turn me blind and stupid, or more stupid. Quite happy to drink this, but if you will forgive me indulging myself, I'm going to call that solution T, and I'm going to add to it a little solution G, which... and I do not fake experiment, I have to tell you. I once gave a presentation like this 5 times in a row, and I really have no idea what I was talking about at the end. So a very good health. Happy Christmas to you all. Well, while I was doing that, and if you didn't see, I might do it again, you might have seen other things about me than the tonic that were fluorescing. You see Dandruff fluoresces if you look there. If I grin at you hideously, you can see my teeth fluoresce. I'm just showing off. I mean, I'm quite old, but I still have my own teeth. And the fact that molecules fluoresce is used very, very widely in biology and in medicine. To do microscopy, to do cell sorting, to do all kinds of things. So any of you interested in biology or medicine, you will certainly come across fluorescence in due course. Now, the fluorescence is quite short-lived. If I take the lamp away, you can see immediately it's extinguished. In fact, it lasts, after the lamp has excited it, for about 1/1000th of a second. So your eyes can't respond that quickly. There are some materials which fluoresce or phosphorus emit for over a much longer time scale. So if we put the lights down, you've probably seen these already while I've been speaking. If I irradiate, another Christmas theme, you see stars. And if I take the light away, they last for quite a long time. Now, which way Nazareth is, I have no idea, but probably not that direction. And this kind of luminescence, of course, has all sorts of uses in the modern world. Well, I'm very conscious we're supposed to finish at about 1:15. Is that somebody confirm that for me? So I'm going to have to get a move on because I've got lots of things I want to show you. What other kinds of luminescence could I show you? Well, there's this one, which is a true all chemists love because it's caused by a chemical reaction. And in order to do it, I need a vessel. And I appear not to have got one, so I'll have to put it into... That'll do. I thought I had a big one, but never mind. So I need the lights really right out for this because it's quite a weak effect. I'll put it along there so you can see it, right? On top of there. Right, can we have the lights right down, please? Ah, now I can't see where to put it. There we go. All right, now we can go down. Okay. And that's like 4, the 2 together. Right. So, that's cold chemical light. People think things that glow must be hot because that's what you learn when you're a child. In fact, this is just pure cold chemical light. And there are all sorts of commercial versions of this. And I brought a couple along. If I just break a stick, mix 2 chemicals together, you get quite a bright light. Anybody confess the voting Tory? There somewhere maybe. Now, I had a whole pile of them. I don't know what's happened. This one, what's that, Lib Dem or green? Or, I'm not going to throw it right back. It might hurt somebody, so I'll just throw one over there. Look, all right? Oh, another Tory. One over that side. Ah, well. Doesn't take much to get your vote, I can see. I don't know why these are all blue. They're supposed to be all sorts of different colours, but never mind. So maybe a sign of something to come. One out there, look. One in the front there. All right. Now, if we can have the lights up. Somebody got there before you. If you will form an orderly queue at the end of this talk, just the children, I have some of these little bracelets and necklaces which are of that sort. I'm quite happy to hand them out. But only if you form an orderly queue, and don't knock all this stuff off when you come down. We'll stand by the door and give them out as you go, all right? So, that is only children, yes. I haven't got enough for everybody. If you can convince me otherwise, I'll see if I can be generous. Okay. Oh, I thought I had some more. Yes, there's a red one. Look, there's a red one. Nah. You have to vote Labour if you had this one. No, look, I'm not going to throw it because I'll hurt somebody, so I'll just leave it there. And that's another blue one, so there you go. Okay, I want to just think about some of the things we might do at Christmas in terms of energy, really. Where do we get our energy from? We eat things, of course, and I'm going to look at that in just a minute. What I didn't do over here, and I want to do, is to remind you that at Christmas time you like things to be cold, don't you? So if I can, without taking too long, just pour out some of the coldest stuff that I have easily accessible. This is liquid nitrogen. It's nitrogen from the air which has been liquefied. And it is very cold. It's minus 196 centigrade. And you can do all sorts of things with it. In the interest of time, perhaps I won't do too much. Perhaps I'll put my glove on for this, discretion being the better for. Here's one I did earlier. You see it's can you see what it is? A banana, yeah. If I'd remembered to bring a nail, I could knock a nail in into here, but I'm afraid I didn't bring a nail with me. So let's just see what happens. brings new meaning to the word banana split, you know. I'm not going to pursue this because we're running out of time, but don't burn yourself because it is very cold. Don't hold it. Yeah. I could be very nasty and do what I used to do many years ago when we had children coming around on open days. If they were really very naughty, I used to take an egg and break it into liquid nitrogen, and it looked just like it was cooked. And then I would say to the particularly naughty child, I'd say, look, put that in your pocket and run home and show your mummy what you've got. See, they didn't come back, those people. Well, you can change the state of things by doing simple physical things like cooling them down. This has a shape, it's flexible, but if I freeze it, and flowers are something that we give each other at Christmas time or we give our loved ones. But people tend to be very fickle at Christmas, don't they? They change their allegiances quite regularly. So here, if I was handing this to a lady, I might suddenly have a change of heart and say, no, I'm not really interested. I need a volunteer to help me with this one. This is somebody from the back, perhaps. Yeah, do you want to go? Yes? 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 Actually, I need two people, so another one. Somebody, all right, you from the front. Now, what I've done is lost... Which? What's that, the banana? It's just a banana. It may be poisonous to some people, but not as far as I know. No, look, I've lost this. We'll have to use these things, all right? The ones I... Just use that as a stirrer, all right? And I'll try and find something for myself to use. I'll use this. Oh, there's another one of those. Right. Okay, now you need to put some gloves on, both of you, right? And I'll put my gloves on here, because we're going to have a race. So what's your name?
Alex.
Alex, another Alex. And?
Matthew.
Matthew and Alex. Right. So we need to put some safety specs on, just to be on the safe side. All right. Now, I've got two liquids here, and we're just going to mix them, and we're going to make some biscuit, all right? We hope. But we're going to see whose works best, right? So when you're all ready and put your specs on, pick them up. And over that blue paper, we're just going to pour one into the other and back again about 6 times, all right? So ready, steady, go. 1, 2, 3, 4, 5, 6. That'll do. So put the full one in the middle. Put it separate. And yours over there, just a bit that. Yeah, not quite as far, because you'll see why in a minute. Now give me the empty ones, and I'll get them out of the way. Now we're just going to stir this. All right. So get your stirrer, whatever it is. Did I not give you a stirrer? There you are. Have a stirrer. And then we're just going to stir it as fast as we can. All right. Here we go. How fast it goes depends on the temperature in the room, but it's quite warm, so it should go quite fast. Mine's beginning to go. Can you see anything happen to yours? Ah, no. Now what? Now can you see? It's rising. Yes, it's cooking. And it is actually cooking, because this is an exothermic reaction. This is a reaction which creates its own heat. And as we'll see, as the heat permeates into the reaction mixture, it makes it go faster. So it goes faster and faster and faster until it's used all the stuff up. Now it looks like a wobbly jelly at the moment, but in just a few minutes it'll be a solid biscuit-like material. However, you cannot eat it. This is the material you put between the cavity walls, in houses, to insulate. It's polyurethane foam, in fact. And we're doing a bit better than you. I wonder why that is, do you think?
Because I put something here.
No, I think it's because you used the wrong end of the stirrer, actually. I mean, quite seriously, it goes fastest when you stir it, when you get the best mixture. So, well, there you are. It's now, what's happening here is that molecules are zipping together, and every time they zip together, one molecule of carbon dioxide is given off, and that foams up the mixture. So while it's still a liquid, you get these bubbles formed, and then as it turns solid, they're trapped inside, and so you get this insulating foam material. Furniture is made with the same sort of stuff, but except it stays flexible in that case. All right, I think we're probably done now. So at the end of this, how are we going to do this? There are 2 of you and 3 of those, and I don't want one. If we only do 2, it usually looks quite vulgar, so I suppose I'd better... Maybe this is a better experiment. All right, I think we'll have to leave it, but you can have a look at the end. You can take it home if you want to, all right? So pull your gloves off carefully, because one of these materials is not very nice. All right, just peel it back over and leave it down. There you go, good. Well, I think we get a round of applause for the loser, don't we? Thanks a lot. I'm running out of time. I'm going to have to speed up. I wanted to talk about the speed of reaction. Now, in order to make that work, I'll have to do it in just a minute. How can you make reactions go faster? You heat them up. So let's look at a chemical reaction that you've all indulged in at some point. Matches. Just burning things, really. Very temperamental. Huh? Right. What can I burn? Well, I could burn wood, couldn't I? I mean, you all burn wood. Not very spectacular. You've all seen it. Interesting to see what's happening. All the carbon there is turning into carbon dioxide. The hydrogen is turning into water. Nitrogen is turning into oxides of nitrogen. Sulfur is turning into sulfur dioxide. These are all just oxidation reactions. And they give out heat, which is why we do it. And they give out light, which is also why we do it. But it's a pretty slow reaction, as you can see. Why is it slow? Well, one of the reactants is oxygen in the air. And I can't really increase the concentration of that. I could make more of the material in contact by using powdered wood. So let's see if it'll work. Now, sometimes this doesn't, so I hope we're not going to be too disappointed, but just have a look. And I have to go around the front here to do this because I don't want to blow it into the audience. Put the lights down and just see. Can we have the lights down? So I'm going to blow this powdered wood through the flame, all right? 1, 2, 3. Didn't work. Didn't work very well. It's supposed to go with a big sheet of flame. I think you need a hotter flame to do it. I haven't got one. All right, let's do something different. Can you increase the amount of oxygen? You can't, I can. Because I've soaked the other end of this stick in liquid oxygen. So it's rocket fuel, if you like. And with any luck, I can make it burn a little bit faster. And you can see, I hope, that with any luck, I can make it burn underwater. Well, that should be, there we go. Sometimes it'll burn underwater. I don't know if this one's going to, actually, but no. Well, failure. Never mind, you saw it went much faster. So could I make it go faster than that? Well, I called this lecture Christmas Cracker, so here's my sort of rather feeble attempt at a cracker. And let's see if we can get the best possible chemical mixture to make the reaction go fast, and that's a mixture of gases. So here we have a mixture of gases. You need 3 hands when you do this lecture. So, well, I did say it was called Christmas Crackers, didn't I? Could you avoid doing that? Could you avoid a reaction requiring an energy source? I had to give that some heat. Well, you could use a catalyst. And catalysts, effectively, they get the energy, the reactions get the energy they want from the room because you lower the energy barrier. No, there's no bang, so you don't have to worry. So one of the things that we break down in our body when we indulge too much at Christmas time is hydrogen peroxide, which is very dangerous for the body. And I've got here a piece of liver, which I should have chopped up, but I didn't. And the liver does what you require it to do. Peroxide in your body is very dangerous. And the liver destroys it by turning it into water and oxygen, which is what is happening there. And you can see it's fairly slow, but if I chopped the liver up, that would have been a much faster reaction. You can do it without using biology, just by using a chemical catalyst. This is manganese dioxide. And so if I put a pinch in there, then you can see it goes much faster. Well, I was going to show you why things burn why alcohol burns on a Christmas pudding, but we haven't got time, so I'll just show you what Christmas is all about, really. If I can find my tongs. Where are my tongs? Oh, there they are. You see what I've got in there? £20 note, all right? Can we have the lights down for this, please? I just don't want you to see me cry, you know, as I do. There we are, £20 note. Lights right down, please. And you can see that burning. All right, we put them back up again now. Well, that's what happens on the Christmas pudding. It's just the Christmas pudding acts like a wick, as this does, to burn the fuel, which is just an alcohol-water mixture. So if any of you young ones want to try this at home, you have to avail yourself of a £20 note from your father's wallet. You have to get hold of his best brandy, and then you set fire to it. But don't leave it too long, otherwise everything will go up in smoke and you won't be very popular. All right. I think we should be almost near the end. We've done those few things, and we're way over time. So I will just do one more thing for you. I was going to sing you a song. But I can't sing you a song without... Yeah. Well, I had some balloons somewhere and I can't see the balloons. So we'll have to use one of these instead, all right? Is there? What, these balloons? On the trolley. There's a balloon. Is there? Ah, right. That will do perfectly. Thank you very much. I couldn't see that. Right. Okay, let's just see.
We wish you a Merry Christmas. We wish you a Merry Christmas. And so on.
So, I'd like to go on for much longer, but I don't think I should because you want to have your refreshments and go home. So I'm just going to see if I can finish off with a few little pops. I have some balloons filled with various things, and I hope that these work. We'll just have to see. It's probably best if we have the lights down a bit. All right. See what the first one does. See what the second one does. Put the match out. See what this one does. See what that one does. See what this one does. Oh, didn't go. Oh, didn't work. Thank you very much.